Well, it is a pleasure to introduce Alex Wein. He is a current instructor at New York University, and he received his PhD in mathematics from MIT in 2018. He has received recognition from his research. In particular, he has been awarded the Johnson Prize by the MIT Mathematics Department in 2018. And this year, he will start as a Simons Research Fellow at UC Berkeley. His research is in statistical and computational limits of machine learning and high-dimensional statistics. And today, he's going to talk about optimal spectral recovery of a planted vector in a subspace. Thank you, Alex, for being with us, and we're looking forward to your talk.
Great. Yeah, thank you so much for the introduction, and thanks to the organizers for inviting me. Yeah, so I'm excited to tell you about this work joined with Chang Mao, who is at Georgia Tech. So let me jump in and tell you a little bit about what problem I want to talk about. Okay, so the goal is going to be to recover a structured vector planted in a random subspace. Okay, so this big N, you think of as sort of the ambient dimension. And then there's going to be some D smaller than big N. And we're going to be given a D-dimensional subspace. And somewhere in that subspace, there is hidden a vector with a certain kind of structure. And we want to find it. Okay, so what do I mean by structure? Well, I'll be a bit vague for now, but one primary example to have in mind is sparsity. So you can imagine that the planted vector is guaranteed to have only a row fraction of entries that are non-zero, so mostly zeros, with a few non-zeros. And even to simplify our lives a little bit further, let's pretend for the purposes of this talk that the non-zeros are basically just plus minus ones, except I'm going to normalize them just so that the entries sort of are constant size on average, or in other words, the norm of V is going to be roughly square root of N. Okay, and so we have this vector in a subspace. One thing that's going to be important for us is that it's sort of a random subspace. Apart from the fact that it contains the special vector V, the rest will be random. And we're going to need to exploit that randomness because otherwise there simply won't be any hope. The problem will just be NP hard if we imagine we had kind of an arbitrary subspace. Okay, so why do we care about this type of problem? I mean, I hope it's sort of well motivated on its own, but this is kind of motivated because it's a generic task in various machine learning problems. So for example, dictionary learning, matrix sparsification, sparse PCA. I won't say too much about this, but you can think of this problem or some variant of this problem as being sort of a key subroutine in solving a lot of these other types of things. But I'm mostly going to be just looking at this problem in its own right. Okay, so let me now define a bit more formally what actually is the model I want to talk about. So how actually do we generate this subspace? So I'm saying y equals b times r. So what is y going to be? Y is going to be an n by d matrix, sort of a tall matrix like this. And we're going to think of these columns as being the basis for the subspace, right? We're being given a subspace as this basis. Right, so this is y, and then the way we construct y, so b means basis, r means rotation. So b is going to be a very specific basis of the subspace. It's again n by d, but the planted vector v is going to be sitting right here as the first column. And then the remaining columns are just going to be random. Specifically, these other GIs will just be normal, Gaussian. Okay. So this, this generates a basis for a subspace that includes V1 and is otherwise random. Of course, V1 is not really hidden. It's just sitting there as the first coordinate. And so to make the problem more, more difficult, we add R, which is a rotation. So this is an orthonormal or an orthogonal matrix, right? Which just, mixes up these vectors, takes linear combinations of them so that V is now hidden. Okay, so is that setup clear? Feel free to stop me anytime. So I'll be basically focusing on this version of the problem, but let me just remark that one slightly harder variant could be if we're not given a basis of this form, but really given an arbitrary basis for this column span of this thing. Right, that problem's a little bit more general because a basis generated in this way is going to be almost orthogonal with high probability because of the randomness here, whereas an arbitrary basis might not be very orthogonal. But it actually turns out that the harder variant is not really much harder than this variant, because if I'm given an arbitrary basis, I can orthonormalize it myself. And then it turns out to be close enough to this problem that with some technical work, we can basically solve it as well. So whenever we can solve this problem, we can also solve this problem. Okay, so I'm just going to focus on this one.
Alex, there's a question from the audience. Is R random or does it matter?
Yeah, great question. You could sort of imagine it either way. Like, certainly making it, if I'm trying to solve this problem, I can sort of assume without loss of generality that it's random, because if I wanted to, I could randomize it myself. I could like put a second R prime here and force it to be random if I want. So yeah, I'm mostly going to imagine it being random, although that's not really essential. I see a raised hand from Dustin.
So is the main point that the image of Y is drawn uniformly from the Grassmannian?
Yeah, aside from the fact that this specific vector V is included.
Aha, great, thank you.
Yeah, so there's this V we're imagining is just like some fixed vector, which we're guaranteed has a certain structure, state sparsity. And yeah, but then apart from that, it's just totally random from the Grassmannian, yeah. Good, thanks for clarifying that. All right, should we move on?
Yeah, I think we're good.
So let me talk a little bit about what some prior work has been has achieved here. So to simplify our lives a bit, let's imagine this type of scaling regime. So n, right, the bigger dimension will go to infinity, and then rho, remember rho is the fraction of sparsity. So this will be some power of n, and then the smaller dimension will also be some other power of n. Okay, and we care about, for what values of a and b can we solve the problem, for what values can we not. So information theoretically, it turns out to always be possible in this scaling regime. If I'm willing to do sort of a brute force search over all possible sparse vectors that might be in the subspace, it's always possible, but of course we are we would like a practical algorithm ideally, one that runs in polynomial time. And so for polynomial time algorithms, there has been a long list of various approaches that give different conditions. Don't worry about parsing all of these right now because I'll draw a picture in a second. But approaches based on linear programming, non-convex optimization, the sum of squares, semi-definite programming, and then sort of a faster spectral method inspired by the sum of squares. And these all, achieve various conditions which are not all totally comparable to each other. And so what our contributions will be are these two things at the bottom. We're going to show that a spectral method, so this simple spectral method here with a small modification, succeeds under some condition. And this condition turns out to be better than all the previous ones. And on the other hand, we're going to actually argue that this is sort of optimal in the sense that we believe the problem is computationally hard when you're not in that regime. Okay, so I'll say later what exactly form this evidence takes, but this is sort of the idea. And just to draw a quick picture of what this looks like in alpha beta space. So the previous work, first we had Demonet and Hand showing that all of this part can be achieved. That's the first one there, right? So I'm using the green to mean easy. Not easy as in it's like trivial, but formally easy in the sense that there exists a polynomial time algorithm. And then the sum of squares method kind of instead cuts off, oops. this piece instead and shows that it's also possible here. So we have kind of these two previous algorithms which are kind of incomparable to each other. And the other two are the other two fall totally within this green region. So before our work, this was sort of the state of the art. This is what's known. And so what we're showing now is that we believe the real threshold is actually across here. So our work has kind of two parts showing that, yes, it is possible in this new region here, and also some kind of formal evidence for why we believe it is hard, computationally hard. So there's no polynomial time algorithm in this area. Okay, does that make sense? So, one of the sort of key insights that made us first realize we were going to be able to make progress on this problem, at least for the lower bound, was actually to reformulate it in a way that that looks totally different, but turns out to be equivalent. So here I have, basically this is the original version of the problem that I talked about already, and I'm going to tell you a new way to think about it, which turns out to be equivalent. So let's recap the original one first, right? This is just, right, if we remember before, y being b times r with the vector v sort of hidden in the first column of b. And let's assume for simplicity that v has IID entries drawn from some mu. So you can imagine mu being like a sparse distribution, for example. So it's 0 with large probability, but then sometimes it's either 1 or -1, or maybe normalized appropriately. And let's pretend R is a random orthogonal matrix. Okay, so that's problem one. That's the first problem. This gives you some distribution over matrices Y, that sort of encoded basis, right? And here we imagine the columns as being the basis for the subspace we're being given. The second version is going to be a bit different because here we're actually going to think more about the rows than the columns. So the way the second version works is we first draw a random unit vector u. So this in d dimensions, right? D is the smaller dimension here. And we think of this as sort of a planted direction. And what happens is that these yi's, so these rows, they're drawn, once you've fixed u, the yi's are just independent samples. Each one is a vector, and what they basically are is that in the hidden direction u, their distribution is mu, right? The same mu from here. But in all other directions, they're Gaussian, right? So there's some direction u, and if I sort of look at the projection of y onto that direction, it's distributed like this special planted distribution mu, whatever that is. But if I pick any other direction orthogonal to this and look at how u is distributed in that direction, oops, it'll just be like a Gaussian. Okay, so are the two versions of this problem clear? Yes, definitely stop me if anything is unclear there. Now, maybe the less obvious thing is why these are actually the same. So the claim here is that these are literally the same distribution over y. And the way to sort of think about it, how does this correspond to that? I mean, one thing that's probably clear is that the v's, these vi's correspond to, I mean, I've suggestively written vi here, right? These things distributed as mu kind of correspond to these ones. But this u, this planted direction u, turns out to correspond to the first row of R. Okay, so the first row of here is U transpose. So kind of what's really going on here is that right, remember this stuff is all Gaussian. So in this model, we're applying this random rotation, but all that really matters is the first row, because the first row tells you what's going to happen to this coordinate, right? What happens to the vector v. The rest of the stuff is Gaussian, so it's already rotationally invariant, so it doesn't actually matter how you rotate it. So this problem somehow simplifies things by saying, okay, you don't have to worry about this whole rotation matrix. It's actually just the first row that ends up being important. Okay, another way to think about what U is it has this this form. So it's the vector that tells you how to recover V as a linear combination of the columns of Y. Right, it's the vector that tells you what linear combination of Y of those columns do I need to get back my original vector. Okay, and so, right, to see that these are equivalent, you know, one can stare at this problem a bit and see that this really will have this same distribution. Or maybe in a more explicit way to write, you know, what is really the distribution of each row yi is like vi times u plus a normal that sort of ignores, you know, this may or may not be helpful, but this is a more explicit way of writing down this. And you know, staring at this a bit, you can see that I'm going to multiply v by u to get this part, and then the rest is going to give you that. Okay, so does this make sense? I hope it's at least plausible that these two would be kind of equivalent. So let me talk a little bit about the algorithm now. So here's sort of the algorithm we're going to analyze. This is very much inspired by this previous work of these folks, Hopkins, Schramm, Steurer, who you know, came up with this spectral method based on inspired by sum of squares. The only part that we added was this correction, which is only important for a few certain values of the parameters. Okay, so what is this? You build some matrix. It's a D by D matrix. Remember what the yi's mean. The yi's are just the rows of the thing that I'm given. So it helps maybe here to think about the second formulation of the problem. And okay, so what are you doing? Like, you know, it's some degree 4 polynomial in these things. You know, this thing has size roughly D, so this can be thought of as maybe a kind of a centering term. You know, we said earlier that these are, you can think of as IID samples from this distribution that has kind of a planted direction. And so it kind of makes sense that maybe you would want to sum over all your independent samples of something. Now, why this is exactly the right something, I maybe can't totally explain, but somehow, you know, the second moment of y turns out not to be helpful, not to tell you anything. And so the fourth moment of y, we're somehow exploiting here the fourth moment of y. And this matrix is somehow designed so that hopefully, if it works, the leading eigenvector is going to be really close to u being this planted direction I mentioned in the last slide. And remember, we said that y times u equals v. So once I've recovered u, I can also recover v easily, and I'm done. Okay. So since this is quite similar. Oh, yeah.
Is there a naive spectral method for this problem?
Oh, good question. I mean, one thing you can do that's slightly more naive is to just look at the norms of these things, like just looking at the norms of the yi's. It turns out under some condition, like the same condition as this Demonnet-Hand result that I mentioned earlier, that just by looking at which rows have the biggest norm, you can pick out where the sparse vector is. But that only works like in a smaller regime of parameters. Apart from that, I'm not sure of like a more naive spectral method or anything. Yeah. Good. So, right, since this, you know, it's kind of similar to this previous work, I want to mention what exactly are our improvements. So one main thing is that instead of they had this condition, and we you know, do a bunch of technical work to improve it to this one, which we believe is sort of the correct condition. We also kind of strengthen the guarantees on what it means to succeed. So the previous work said that with high probability, you can estimate V well in the L2 norm, and we kind of upgrade this to L infinity norm, which in particular means that you can, with high probability, exactly recover the support of V. The proof of this is actually one of the most technically difficult parts of the paper and involves a leave one out analysis, but I will not try to get into the details of this too much. And finally, one more thing is that we treat things in a bit higher generality. So I know earlier I said that rho should be like little o of 1, it should be like a small power of n, but we actually also can take rho to be like a constant. So for example, if rho is 1, and we're just talking about a planted plus minus 1 valued vector in a subspace, this seems to be a problem that people have maybe not really studied before, but we can also solve this using the same method under this condition, and sort of conversely, we believe it's hard otherwise. And more generally, we can handle a more general type of structure on the V, which will be more clear on the next slide. Okay, so let me try to say briefly maybe like how one can hope to analyze this spectral method, or sort of what's really going on behind the scenes here. So the way one usually analyzes these types of things, you have some matrix and you want to show that it has kind of, you break it down into a signal part and a noise part. And you want to show that the signal part is a large rank 1 component, a large rank 1 thing, where sort of, which will dictate the top eigenvector. And then the noise is sort of smaller than that in spectral norm. So in this case, if we look at the expected value of m, so kind of fix u, fix this hidden direction that we want to recover. For any fixed u, the expectation of this matrix turns out to be a thing you can compute. And it's designed so that it's a rank 1 thing with u as the vector here, which is going to be good for our purposes, right? But then we have this thing. This we can think of as kind of a signal to noise ratio. And what it really is, to interpret it, you should note that for just a Gaussian vector, the 4 norm of a Gaussian vector turns out to be 3n, or 4 norm to the 4th. And so this is really measuring how much does the 4 norm of our planted vector differ from that of a Gaussian vector, right? And that's sort of what dictates the signal strength. So if our planted vector has a 4 norm that's very different from that of a Gaussian vector, that's going to be great for us, right? We're going to have a big thing here. Either a big positive thing here or a big negative thing here would be helpful, right? Either that will mean either our top eigenvector or bottom eigenvector will be helpful for recovering u. And then the other step is just to show, the rest. We basically want to show that m concentrates well around its expectation. So if you take this other random part, other noisy part of the matrix, with high probability, we need to use a lot of, with high probability, you want to show that this is small in spectral norm, right? That its top eigenvalue is bounded. Okay, so this is kind of the technical step that involves all sorts of matrix concentration and so on that I won't try to get into. And this is kind of crucially where this centering here is important for kind of controlling the norm of this random matrix. Okay, and then so putting it together, we're in great shape as long as the spectral norm of this part is bigger than the spectral norm of this part, right? Because that will mean our matrix is approximately a multiple of u transpose, and so its top eigenvector will be close to u. Okay, so putting it together, we get some condition. So more general than what I put on the last slide. So, we just need our 4 norm to be different from that of a Gaussian vector, and we need some other condition. This one here kind of turns out to be the important one, and the other one is only important if V has kind of entries of very different sizes. And so one can specialize this to the sparse Rademacher vector I talked about before, and recover, the thing I mentioned earlier, right? This is the condition I gave you earlier. And we also have this condition that rho should be bounded away from 1/3, right? 1/3 is the magic value where the 4 norm of the sparse vector happens to be the same as that of a Gaussian vector. So in this case, so this method won't work, but otherwise it does work. Right, so this kind of illustrates, there's nothing special about sparsity. It's really just about having a 4 norm that's different from that of a Gaussian. As long as you have that, we're in good shape. Good, any questions about this? So if not, I want to now switch gears to the other side of the coin, which is the hardness part, right? So we now have some algorithm that works up to a certain threshold. And we want to ask ourselves whether we can do better. And so we want to show in some sense that we believe it's computationally hard to do better than this. This is something we can't hope to prove outright, right? It's too much to hope to actually prove like there is no polynomial time algorithm that succeeds here, because this simply is, beyond the reach of current complexity theory. We don't have tools for these kinds of average case problems, even if you're willing to assume something like P not equal NP. So the approach we're going to take instead is going to be to look at the class of spectral methods. Okay, but first, actually, one other thing before I get there is that it's sufficient to think about hardness of what's called the detection or testing problem. Right, we're going to essentially think instead about hypothesis testing between two distributions. So this first one is going to be the planted distribution. It's the same distribution I've already showed you on a previous slide, right, where there's a planted vector. And this Q is the null distribution, which is where Y is just totally random Gaussian with no planted anything. And so the detection problem is about whether you can even tell these apart, right? I'm going to give you a Y that's drawn either from P or from Q. You have to tell me which one. And you want to succeed with high probability. Right, and the point here is that if we can argue that the detection problem is hard, this would imply that the recovery problem is hard. Formally, this takes the form of a polynomial time reduction, but hopefully this is like very intuitive as well, that like if you cannot even tell whether there is a planted signal, you cannot possibly hope to recover the planted signal. Okay, and so that idea can be sort of formalized. So we're just going to focus on this distinguishing question. And so, and we're specifically going to think about like how well can spectral methods, the whole class of all possible spectral methods, solve this distinguishing question. So just to recap what we already know, right? We already know that there is some spectral method. And what does it look like? It's a D by D matrix, and every entry of it is a degree 4 polynomial in the entries of Y. Right? We observe this thing Y, and it just has, n times D individual entries. We're kind of thinking of those individual entries as our input variables. Right? And so each entry of this, each Mij, is some degree 4 polynomial, multivariate polynomial in like all of these values, right? You cannot have degree 2 coming from this part and degree 2 coming from this part. So that's one property of the spectral method we already know we have. And something that one can easily get from the analysis I talked about already is that this spectral method does successfully solve the detection problem as well, the distinguishing. And the way you do it is just by thresholding the spectral norm of this matrix, right? Or in other words, the largest eigenvalue in magnitude. Right, from what I said previously, if there is a planted vector, there's going to be some big rank 1 component in our matrix that will cause us to have a large eigenvalue. On the other hand, if I give you a matrix with no planted vector, the spectral norm is going to be smaller. Okay. And so this kind of begs the question, like, why this specific choice? Maybe I could design a better spectral method by doing, any number of other things. I could pick a different polynomial instead of this particular one, maybe higher degree, maybe a 6 degree polynomial or 8 degree or something instead of 4. Right, there seems to be this whole space of possible spectral methods I could look at, and it seems kind of hopeless to look at them one by one and try to analyze them all. But we are going to nonetheless sort of give an answer to this question. We're going to prove that any spectral method, as long as it's sort of polynomial-sized matrix and its entries are constant degree polynomials in the input, any such spectral method cannot distinguish, must fail under this condition. Okay. So in this sense, we're going to show that a whole class of spectral methods cannot do better than the condition we already have.
Quick question. So do you expect that the higher degrees relaxations, the sum of squares, will not give you any significant different performance, or what's going on here with the higher degree sum of squares? Or will it give you a better constant, but not better performance overall?
Yeah, that's a good question. Yeah, so what I'm saying here does not formally relate to higher degree sum of squares. Yeah, my conjecture, I'll get to this a little bit later, but because of this result, I would sort of be inclined to conjecture that no polynomial-time algorithm can do better than this, including sum of squares and so on. So yes, that would be my guess, is that higher degree sum of squares cannot do better than this, but this is not something that we formally know how to prove.
Thanks.
Yeah, so, right, so what exactly is the theorem? So here's a more formal theorem statement about the limits of spectral methods. So this is sort of in the easy regime. This is saying that in this regime, there is a spectral method that succeeds, right? There exists a D by D matrix, the one I told you about earlier, and some threshold at which to threshold the spectral norm, such that, under planted distribution, the spectral norm of the matrix is going to be big with high probability. Under the null distribution, the spectral norm will be small. And we even have sort of a factor of 2 gaps, so they're sort of very well separated. Right, and this is like a super small probability. And then on the other hand, this is something we kind of knew already, but now we have the strong converse to this, saying that on the other hand, if you're in this hard regime, then, okay, no matter what constants you take, there is no spectral method, right, of polynomial size, of constant degree, that succeeds. Where, here's the notion of what it means to succeed exactly. It's saying a similar thing to before. It's saying that under planted and under null, you can't separate these 2 spectral norms even by a factor of 1 plus epsilon. The main sort of weakness in this result is right here, is the error probability. So, ideally we would rule out any spectral method that succeeds with high probability, even like 1 minus little o of 1. Instead, we're only able to rule out spectral methods that succeed with, some specific high probability. But, luckily this specific probability is not too restrictive, because in the easy regime, we can succeed with like a much better probability than that. So this is, kind of a technical weakness, but hopefully not too serious. Right, and so putting these 2 sides together, we've sort of established that this threshold is the precise threshold for all possible spectral methods, subject to all these technical conditions. Right, okay, so this really suggests that there's a fundamental barrier at this point, and that if we want to go past it, we need to find an algorithm that's doing something quite different from what we have been doing so far. Okay. So,
actually, Alex, if you don't mind, just a quick question. So
yeah.
for the easy regime, is the degree 4 required? Like you cannot get away with a lower degree polynomial?
Good question. Yeah, I believe that's true, because I think that the first 3 moments basically just don't tell you anything. Like as long as the planted vector has a norm that is the same as that of a Gaussian vector, yeah, like right, at least if we're looking at these sparse Rademacher type of vectors, it matches moments with a Gaussian, like the first, second, and third moments match that of a Gaussian. And so from the third moments alone, you sort of can't see anything, but once you go to the fourth moment, you start to notice. So I believe that yes, degree 4 is required, although I don't know if I have exactly a formal statement of this.
Okay, got it. Yeah, thanks, that helps. Thank you.
Sure. Yeah, good. Any other questions?
Doesn't look like it right now.
Yeah, so let me try to give you some idea of how to prove this type of thing. How would you prove that like all spectral methods fail in a certain regime? There's going to be 2 steps, and this is going to leverage the idea of thinking about the whole algorithm as a low-degree polynomial. And so the first observation here is that if I have any spectral method of this form, and I want to think about what will its spectral norm be, or its max eigenvalue, that I can sort of write this as a low-degree polynomial. So here I'm thinking about polynomials that take in the entire matrix Y as input, right? So just multivariate polynomials in n times d variables, and they just output a number, right? And for a given matrix, the specific polynomial I have in mind is that is to take the trace of my matrix raised to a big power. And the point of this is that when you do this, you get the sum of eigenvalues raised to this big power. And if the power is big enough, it's basically just the maximum eigenvalue that will dominate here. So as long as I raise it to a power that's something like log of the dimension of the matrix, this polynomial will be a reasonable approximation of the spectral norm raised to the 2q power. Okay, and so the total degree of this polynomial that I said here is sort of logarithmic, right? Each entry of m itself is degree k, and then we're raising it to the 2q power. Right, so the first claim here is that a spectral method can sort of be implemented as a logarithmic degree polynomial. And then the second part is to sort of say, any polynomial of that type, any logarithmic degree polynomial, of course, when we're in the hard regime, any polynomial of that form of logarithmic degree somehow fails to solve the detection problem. Okay, and what specifically do I mean fails to solve detection? This is the particular formal sense in which we are able to show that no polynomial can succeed. So, what's going on here? This thing I'm calling sort of the degree d advantage is somehow measuring, whether or not there's a degree d polynomial that can separate p and q well. And what this thing is here is just, here's the expectation of my polynomial under p. The bottom you can think of as sort of the size of the fluctuations of my polynomial under q, or like the standard deviation, more or less. And if we're able to show that this value is bounded, right, that it's not too big, this is like saying that no matter what polynomial I take, my mean value implanted is not going to be too much bigger than my fluctuations under the null. And so I'm not really going to be able to separate these two hypotheses consistently. Okay, and it turns out, hopefully it's sort of believable enough that once we've proved this, we can combine it with this idea to prove the statement on the previous slide, right? We can say, like, suppose there were a spectral method that succeeded well, now we're going to construct this polynomial and show that it basically would achieve a big value here. We're assuming it succeeds at distinguishing in some technical sense. We can use that to show that this value would then have to be big as well, which would contradict the fact that we know it's small. Okay. So that's sort of a rough proof sketch. And so of course it now boils down to this, right? How do we show that all of these low degree polynomials fail, right? It seems maybe we haven't made progress or that we've made things even harder for ourselves, but it turns out we will be able to control this. I should say a bit about like the history of this thing, right? This is not really something new, but rather falls into a long line of work on these low degree polynomial lower bounds. This value here also has a few other names. It's being called a few of these different things. This means like the likelihood ratio projected onto the space of low degree polynomials. And this means it's sort of the low degree, oops, there should be a less than D here, the low degree chi-squared divergence. But okay, I won't get into those connections really. But all of this previous work has sort of investigated this question of, for any given problem, figuring out when can low degree polynomials solve it and when can they not. This started kind of from the sum of squares, the pseudo calibration method in sum of squares, and it was made a bit more explicit by Hopkins and Steurer and others, and in Sam Hopkins' PhD thesis. And for more on this, there's a survey article that I've written with Tim and Afonso about this. And basically, I think this area is very exciting because it has now been shown that for all kinds of different problems. So, this big list of problems that are somehow a signal plus noise, some kind of planted structure hidden in some kind of high dimensional noise, planted clique, sparse PCA, the stochastic block model, et cetera, et cetera. For all of these problems, we've now sort of been able to show that low degree polynomials succeed in the easy regime and provably fail in this sort of conjectured hard regime where we believe there may not be any algorithm. And so low degree polynomials kind of provide a unified explanation for what makes all of these different problems hard. Okay, and so for this reason, we kind of believe, conjecturally at least, that if a new problem comes along and we're able to show that low degree polynomials fail, this sort of constitutes evidence that, maybe any polynomial time algorithm should fail. Of course, there are some caveats to this. There are some limitations to what types of problems this applies to. This informal conjecture I just stated is really for problems that are somehow morally similar in spirit to these types of things. There are a couple counterexamples like XOR SAT. You could solve it with Gaussian elimination, but this is not a low degree polynomial. But somehow Gaussian elimination is a very brittle algorithm that is not useful when there's even a small amount of noise in the problem. And so, really for quite a lot of problems that are these natural high dimensional statistical problems with some noise in them, we don't know any better algorithms than what low degree polynomials can do. All right. So for the rest of the time, I'll get a little bit more into a few more technical details about like how you would prove lower bounds on this thing, or really an upper bound on this quantity, unless there are any other questions about this. All right, so one thing I'm going to mention a couple of times in the future are the Hermite polynomials. So these are polynomials that are orthonormal with respect to Gaussian measure, right? So these are here the first few Hermite polynomials. The point of them is that they have this particular property that if I take expectation over just a Gaussian of two different Hermite polynomials multiplied together, you just get either 1 or 0, right? You get 1 if it's the same k equals L and 0 otherwise. So these polynomials are sort of orthonormal in this sense. You can also use, by taking certain products of these things, you can construct multivariate Hermite polynomials as well. You don't even need to worry what alpha is really indexed by. But these are polynomials that take in multiple inputs and output one number. And again, have the property that like if all the inputs are just IID Gaussian, you have the same sort of orthonormality. Is that okay? And so I want to give like a quick sketch of, how can one even hope to prove something about this, right? a priori, it maybe seems pretty tricky because you have maximum over all possible polynomials. And so, how might we deal with that? But luckily, the specific way this is defined, it turns out to just boil down to a matter of linear algebra. Okay, and so remember, Q is just IID Gaussian for us. And what we're going to do is take, any polynomial f can be expanded in this basis of Hermite polynomials, of multivariate Hermite polynomials, right? So these f hats are like the coefficients, or sort of Fourier coefficients. This part just means that these things are a basis for the degree d polynomials. So we're only taking sort of the degree up to d Hermite polynomials. Right, so any polynomial can be expanded like this. And now we're just going to look at this expression and sort of write it in terms of these f hats. Right, so what's the numerator? It's this. I can plug in the expansion of f and get something. And the point is that it's just linear in f hat. Right, so you can think of it as just being the f hat vector inner product with some specific vector c, where c is just defined to be this thing. This is c sub alpha. Okay. Right, and so what is it? This is expectation under planted distribution of a particular Hermite polynomial. I can similarly kind of just expand out the denominator, right? Plug in the definition of f. And here, crucially, it's important that these h's are orthonormal with respect to q. Because when I expand this out, all the cross terms will go away. And I actually just end up having the norm of f hat as a vector, right? Sort of like a Parseval type equality. Right, so the denominator is really just the norm of the f hat vector, right? The sum of squares of the coefficients. And so now we've reduced this thing to actually a very simple looking thing, right? Where now we can just think about maximizing over these vectors, a vector of coefficients of, inner product of f with some fixed thing c divided by the norm of f. And we all know that the answer to this should just be to take f equals c. And so plugging that in, the actual value of it will be the norm of c. And if we just remember, how c was defined, we get this explicit equation here. Right, so this value here can actually be sort of computed explicitly as long as we're able to compute the expectation under a planted distribution of various Hermite polynomials. Okay, so hopefully that gives you some idea of why this is a tractable thing to analyze. I'll say one quick thing about the specific problem we are looking at here. A key lemma in our result is to give sort of a general low degree analysis of problems of this form, where you have a planted non-Gaussian direction, right? By which I mean this same problem I've put on the slide many times, right? In the planted distribution, you have this random vector u, the planted direction, and here we're actually going to imagine u can be drawn from any distribution. It doesn't have to be a uniformly random vector on the sphere. It can be the planted direction itself can have any sort of prior distribution over unit vectors. And then again, then you get sort of these IID samples, which have distribution mu in the planted direction and otherwise Gaussian. Okay, and we want to distinguish between this and just pure Gaussian noise. And sort of the key technical lemma is that for any problem in that general setup, we can actually give an exact formula for the advantage. So this turns out to sort of nicely decouple into something that only depends on u, right? This only depends on the planted direction. This means like two independent copies of the planted direction drawn from the prior. And then this part depends on mu, on the actual planted distribution. Right, this is a bit of a nasty sum, but at the end of the day, what matters here is like expectation under mu of various various single variable Hermite polynomials. Okay, and so once we are able to establish this technical thing, the rest is not so hard. We can just now, for our specific planted vector problem, plug in, plug things into this formula and sort of bound it. Okay, and the way you can prove this is morally, it's along the lines of what I showed on the last slide, right? The way I showed you could bound this using linear algebra. We play a few extra tricks to simplify some of the calculations. It turns out you can break it into pieces and sort of use a different Hermite basis for different parts of it, so that the Hermite basis kind of aligns with these U's, but I won't get too much into that. Okay, but sort of the upshot of this is that, if you ever have a problem of this form and you want to know if it's easy or hard, here's sort of the answer. Plug everything into here, and you should be able to figure it out. Okay, so that is about it. I'll just sort of summarize the main points. So we looked at this question of a sparse vector that was planted in a d-dimensional subspace of Rn. One of the key insights for us was this reformulation, to actually think of it as this different version of the problem where you have IID samples and each one has distribution mu in a planted direction u. This was, helpful at least for the lower bound. And okay, so on the algorithmic side, we improved the previous analysis to get this condition, or more generally something depending on the form. And then conversely, we sort of show that no spectral method can do better than this when you're above this threshold. Okay, and so this, we've shown that no spectral method can succeed, and also that more generally no low degree polynomial can succeed in this regime. So this problem sort of has a low degree barrier similar to these other problems like planted clique, sparse PCA, et cetera, et cetera. And so for this reason, we are inclined to conjecture that there should not be no polynomial-time algorithm exists in this regime. But of course, that is a conjecture that's, maybe merits further investigation. All right, and that's all. Thank you for your attention.
Thank you, Alex. Very, very nice talk.